Okay, so this is a discussion of Faraday's law, including the calculus. So here it is. This is Faraday's law. So this is saying that you can get EMF that's every bit as real as if you connected a battery to a circuit, except for there is no battery. The EMF source is from a changing magnetic flux. And so what you see, of course, is that we've changed this into a derivative, so any time rate of change of the flux gives you EMF. And this minus sign right here, this is the mathematical encoding of Lenz's law. We usually tend to take care of that separately anyway, so really what we're mostly looking at from this equation is to give us an amount of EMF. We don't necessarily need any sign, but if you want to handle this with some mathematical sophistication, basically this is what makes sure that the this is the way that you mathematically take care of the fact that the current will always be induced such as to fight the change. In most of the examples that you're going to see, this form is totally okay. So it says okay mostly here. You don't necessarily need to take the derivative, it's just the change in flux over change in time, so you can do it that way. And then you can take the absolute value signs here just because what you're really looking for this equation to produce is a number for the EMF. You'll take care of the direction of the induced current separately. So this is okay mostly. Very rarely will you actually need to take a derivative, and very rarely will you actually have to care about the minus sign here. Because you're going to figure out the direction of the induced current in a different manner. What you're mostly going to use this for, again, with Ohm's law, you're going to figure out the induced current direction with that. So over here, associated with the EMF, so we kind of think of that as kind of like voltage. Of course, we know that there's a relationship between voltage and electric field. So there is an electric field that goes along with this. And so we should take a look at that. So it's really easy to get what the electric field is doing. Let's say we have a conducting ring or something like that. And we have figured out that whatever's going on with the changing flux, we figured out that the induced current flows clockwise. So if you figured out that the induced current goes clockwise, of course current is made out of a bunch of plus charges. So we can imagine this whole conducting ring as being filled with a bunch of plus charges, and current is the direction that they flow. So at this point, we can very easily jump to what the electric field must be doing. We know that positive charges like to go downstream to an electric field, so if the charges are moving this way, then they must be following an electric field that points the same way. So just like that, we have gotten what is the electric field doing. So the induced electric field is counterclockwise, or sorry, this is clockwise, because that's the same as the direction of positive charges. Positive charges that make up the current like to go downstream to an electric field. So just like that, we have figured out the direction of the induced electric field. And as far as how to get its amount, well, if this is a circle of radius r, well, this basically, you can see if what this says is it's a closed line integral. So if we are making a loop around like this, and we integrate the same way as the field, we will get that this is just E times L and E times 2 pi R. And so that's pretty much it. If you know the EMF, you can divide by 2 pi R and you can get the electric field. So we'll do some examples of that in future videos, but for right now I just wanted to say some more general remarks about this electric field. It is a weird electric field. It is not like the electric fields we've seen before. Let me compare that to some of the electric fields we've seen previously. So we've seen electric fields, we've never seen them actually form a closed loop. So why is that weird? Well, let me compare that to an electric field we've seen previously, like this. Now, this is what we call a non-conservative field, and this is what we call a conservative field. So let me talk more about the conservative field first. That's probably the easiest. So we know that electric field points from higher voltage to lower voltage. So electric field points the way, and so we can think of this is what's called a conservative force, and then of course it has a associated electric field, just the force per charge, that's the electric field. And of course we know that there's an associated, with any conservative force, is an associated potential energy, or of course we can talk potential energy per charge, which is voltage. So this whole scheme makes sense. This is a conservative force, so there's an associated field with that, and you can of course define a potential energy or a potential energy per charge or something called voltage. So this all makes perfect sense. So as an example, if I take a, let's say, positive charges like to go downstream to the electric field, they like to go to lower voltage, but let me throw it up here. So against the way it goes, it's going to kind of go up and then come back down. So it's very similar to throwing a ball up in the air. In fact, I'll draw that example below here in just a moment. But the way to think of it is that when the charge is on its way up, of course, it's feeling a force against the field, or it's feeling a force with the field, so that's against the motion. So here, we're going to get negative work, and the kinetic energy is going to get converted into what we call potential energy. And then it's going to slow down, it's going to stop, and then the process is going to reverse. We're going to get positive work, and the potential energy gets converted back out to kinetic. So we get that energy back out. So it makes sense to say it went into storage, because of course went into storage where we can then promptly retrieve it. So this is positive charge is going to slow down, stop, speed up, and by the time it comes back right here, it's going to be going exactly the same as the launch speed, but just in the opposite direction. It's pretty much the same thing with gravity. So I guess on this row I'll do the electric stuff, on this I'll do this line I'll do the physics 1 stuff. If I throw a ball up in the air, goes up, comes back down, and this is a side view of a ball being thrown up in the air. And so on the way up, gravity pulls against you, does negative work, converts kinetic energy to potential energy, then you stop, and then it reverses the process, does positive work, you get that energy back out as kinetic. And in fact, by the time you get back down to the same level, you're going exactly the same speed as when you launched it. So we have that energy in both of these cases gets converted from kinetic to potential, and the whole reason we call it potential is because, of course, you can then retrieve it. So you can put it there for storage, stored or potential energy, and then you can retrieve it. So let's go ahead and say what's so weird about this. So this electric field forms a closed loop. So if electric field points to lower voltage, well, where's the lowest voltage here? This thing closes up, so how can it point from higher to lower voltage? Where's the highest? Where's the lowest? This thing forms a closed loop. That's clearly very weird. So this is going to be a totally different thing. The whole idea here, this is a non-conservative force. You can still have an associated electric field. However, the whole concept of potential energy and therefore voltage makes no sense. So what's going on here? What do we do? In fact, this is a good juncture here to point out. Let's say I did go in a closed loop here. I decided I was going to travel in some sort of closed loop and end up where I started. So looking at this relationship, integral of E dot ds, oops, let me not make it a closed loop yet, so let me reserve that for a moment. E dot ds generally gives me delta V, right? If I travel around and I travel around relative to the electric field, I'll get a change in voltage between the endpoints. So if I say I went from here to here, of course, in my travels, I would experience the change in voltage. Now let's make it a closed loop. That's what this little symbol is on the integration side. This means a closed loop. Well, of course, I've started and ended exactly the same place, so whatever voltage it was when I started here, it's still the same thing when I return. So of course, in a closed loop, I would get 0. So delta V in a closed loop would be 0. And in fact, we have a name for this. This is called Kirchhoff's loop rule, right? The whole premise of Kirchhoff's loop rule was that if you go around in a closed path, of course, the sum of all the gains and drops in voltage you experience have to neutralize out to 0. So, what do we do over here? Well, if I go around in a closed path here, I'm not sometimes traveling with the field and sometimes against the field. I'm always traveling with the field, so I will definitely get something. So the integral of E dot ds, or in this case I'm calling it dl, I don't know why, dl, ds, same thing. So if I go around in a closed loop, I'm always traveling with the field. I will not get 0. In fact, what I get is the EMF. So EMF is something now that we can start to understand as a distinct quantity from voltage. So we've sort of characterized voltage and EMF kind of interchangeably at this point. There hasn't really been a need to distinguish them. However, there is a reason why the EMF character exists. Essentially, what the EMF character is the non-conservative version of voltage. Okay, so non-conservative version of voltage. Okay, non-conservative voltage. So essentially, while the whole thing of voltage or potential energy per unit charge doesn't make sense because there is no potential energy, you can still talk about this. Now, what is this? What this is, remember the units of voltage are energy per charge. Okay, so that would be joules per coulomb or volts. However, now that energy per charge is not a conservative type of energy, it's not potential energy, it is non-conservative. Okay, so let me talk about the closest analogy from Physics 1 for that. So let me draw a top view of our flagship non-conservative force from Physics 1. So I've tried to have the non-conservative forces here, conservative ones here, and then Physics 1 on this column and electric stuff on this column. So let me try to show you the best analogy, or a analogy I can think of. Let's say I'm sliding a box across a table. So I'm watching it slow down, slide at the top view of watching it slow down as it comes to a stop along a table, something like this, because friction is stopping it. So of course here, friction does negative work, it converts kinetic energy. We don't call it potential energy, we call it thermal energy. That's what friction does. Kinetic friction takes kinetic energy to thermal. And this is not stored, we certainly are not going to get it back, right? So kinetic energy goes to thermal, and we are certainly not going to retrieve it. That's the whole purpose of why we can't call this a potential energy. To say that it's stored is silly when you can't get it back. So this thing, this object is just going to stop dead, and of course it's not going to come back. If you did push it and push it back the other way, of course, friction would again do this exact same thing. So it would do negative work, and it would convert some more kinetic energy to thermal. So it's certainly not storing energy, it's just a one-way street. It's always taking your kinetic energy, never giving it back. So it would not be proper to call this thermal energy potential. Okay, the whole idea of potential is stored energy so you can get it back. Okay, so what do we have here? The electrical equivalent is that these charges are basically always following the electric field. They're always being given energy. Okay, so instead of friction here, which is a non-conservative force that always takes energy. These are always being given energy, okay? So what you will get is that you will always have energy being given to these charges. And ultimately where it comes from, of course, is you're doing something else in the environment to change the flux, but you are giving these things, you're adding energy to the charges. So essentially, the deflux dt is causing, you're transferring energy somehow from the environment, you're adding energy to these charges. And what this represents, this EMF, this is actually when you do one full lap, okay, this is how much energy each charge gets added. So for instance, if you found that this was, for example, let me go over here, let me say that you found that the EMF was 3 volts. Well, that's 3 joules per coulomb. It literally means that every lap, each of the charges are being given 3 joules for every coulomb, okay? So it is still an energy per charge, it's just not a potential energy per charge, right? There's not stored energy here. In this case, they're being given that from the outside environment every single lap. This literally means you get 3 joules per coulomb for every lap around. And you go around again, you'll get more. And you'll go around again, you'll get more. Now, if this seems like a perpetual motion machine, they just go faster and faster and faster, of course, it's simultaneously being dissipated out to heat, because these charges are not moving through nothingness, they're moving through a conducting ring. And as we learned, the whole process of Ohm's law is that the motion of the charges does get dissipated out to thermal. So they're not actually going any faster, they're just giving that energy up to thermal. So as they go, that energy is dissipated, okay? So as we learned, when charges are moving through a resistor, they're not actually going any faster or any slower. But in this case, the outside environment is adding energy per lap. That energy is being dissipated to thermal, but there's nothing here that's going into storage, okay? So the whole idea of potential energy doesn't make sense in this scheme. This is a weird, non-conservative electric field, okay? It forms a closed loop. So the whole idea of voltage doesn't make sense, and its non-conservative equivalent is EMF. Now you may remember we also used EMF when we're talking about a battery. That's because a battery essentially does the same thing, right? When we're talking about a battery, I sort of characterize EMF at first as just some special character we reserve for the voltage of a battery, but essentially, if you think about it, we have this charge carrier. It goes through here, and when it goes up here, we sort of talked about the battery acting as a pump. It's adding energy. Every lap, it adds energy back to the charge and recycles it back up to a higher thing. And then from here, of course, we can use Ohm's law and our normal voltage stuff. But while the charge is being pumped up from a lower voltage back up to a higher voltage, of course, that is something that a charge would never do unless there was some energy source. In this case, of course, the energy source is the internal chemical reaction of the battery. In this case, the energy source is that some outside entity is changing the flux. But in each case, every single lap that you go around, you will have more energy added back to the charge, and that energy per charge, which is in units of voltage, is called EMF. Just don't actually call it voltage, because of course voltage is reserved for potential energy per unit charge, and the whole construct of potential energy doesn't make sense here. So that right there is kind of an overview of how of Faraday's law. And this conceptual stuff aside, conservative versus non-conservative, hopefully this tied into stuff that you were already learning in Physics 1. As far as how to actually execute on this, the only time that you actually need to do any computation, you'll pretty much be using this. So if you have the EMF, then you divide by 2 pi r, and you get the field. Remember that this field is generally going to form a closed loop. It's this weird non-conservative thing, and the easiest way to get the direction of that induced, that electric field is the way that the current is going, right? Because positive charges like to follow electric field. I should also mention that this induced field is only needed when the actual charge carriers are picked up from rest. So when the plus charges start from rest, okay? So of course, that is the only situation where we cannot use magnetic stuff to explain that. A magnetic field can only deflect existing motion, but here the charges start at rest, just pick themselves up into a current. We do need to invoke an electric field to pick them up. So you may find there are other situations where you don't need electric field to explain the motion. Most notably, there was that there's a motional EMF example, which is like a bar sliding on a track. There you don't need to use electric field to explain why the current flows. You can just explain in terms of purely magnetic deflection. I know this is getting a little bit wishy-washy what to do, but that of course comes from the fact that we're starting to blur the lines between electricity and magnetism, and one person's perspective may differ from another. So if you, from your perspective, the charges start from rest and then they pick up into a current, it's an induced electric field that did that. So let's go ahead and use this as a jumping off point to kind of summarize the whole class. So if we look over here, I've sort of started a summary of how we can make these various fields. Of course, we know that charges can make electric fields, and of course those electric fields are perfectly normal and well-behaved, conservative fields. And we just learned that you can also make an electric field using a changing magnetic flux, and it's kind of got this weird character. It's non-conservative. But these are your two ways to make an electric field. And let me start a chart over here on what laws help you do this. And over here we have brute force integration. And then we have another column for these kind of symmetry laws. And these symmetry laws, of course, are your flux and your line integrals. So these are really nice, quick ways to do things if the symmetry is there. Of course, for brute force integration, we basically break down Coulomb's law. And then for the symmetry version, we use Gauss's law, basically to say, how do charges create electric fields? The law that helps us to figure out how magnetic flux causes an electric field, that is, of course, Faraday's law. And we just learned that one. And then going over here to the magnetic side, the law that helps us with what current causes a magnetic field, the brute force version, is Biot-Savart. And the highly symmetric version, if you can get the symmetry you need, is Ampere's law. And there seems to be one missing. So are there any other ways to make a magnetic field? Yes, in fact, it turns out anytime you wiggle one type of field, you make the other. So here, you wiggle the magnetic field, make an electric field, and it would be nice, of course, if you wiggled the electric field and made a magnetic field. You might ask, that would be nice for symmetry purposes, if that could happen. Yes, you can. Now, this is not in any of our laws so far, so I have to tell you something. Ampere's law, as I gave it to you, is actually not correct, or I should say it's not fully complete. So this is how I characterized Ampere's law for you before. A current causes a magnetic field, but it turns out there is another way to make a magnetic field, and that is through electric flux. So you can see a changing electric flux also makes a magnetic field. This right here, this was not part of Ampere's law originally. In fact, someone named Maxwell fixed this. And so Maxwell was the first person to realize that there was something missing from these laws. And in the process was the first person to actually fully describe electromagnetism. These laws, so these are called Maxwell's equations. So Maxwell's equations are Gauss's law, Faraday's law, Ampere's law with the fix, which of course was the thing that Maxwell did, and then I guess the final law, which is Gauss's law for magnetism, which we talked about briefly as this kind of law that's pretty useless for computation. It's your no magnetic monopoles rule. So these four laws were called Maxwell's equations. If you're wondering why they're called Maxwell's equations, when these are a bunch of laws figured out by other people, he was the first person to fix one of the laws and in the process correctly describe electromagnetism as a whole. Okay, so this describes electromagnetism as a whole. Okay, now what's the big deal? Well, essentially Maxwell's equations is what this whole course is based on. Now if we get a chance, we'll of course take a look at Maxwell's correction and see how to compute, but what I wanted to kind of show you is that this is a summary of the entire course thus far. Okay, so these laws of course form the basis of everything we've talked about this far to some degree, some applications. And you can see the kind of beautiful symmetry there is. So electric fields, of course, can be made in two different ways, either by charge itself or by wiggling the other type of field. And magnetic fields can be made in two different ways, by current or wiggling the other type of field. And of course here we don't need to say if this is conservative or non-conservative, because of course this is always deflective. So it can't do any work in the first place, so we don't have to ask what kind of work it does. Now the big thing that came out of Maxwell's equations is that if you take these laws and with everything fixed up, this actually leads you with a few lines of vector calculus to realize that electromagnetic fields travel in waves, and this is light. So in fact, Maxwell was the first person to realize that light wasn't a completely separate field of study. In fact, it was an application of electromagnetic waves. And of course, what I mean by light is not just restricted to visible light. You could talk about radio and TV waves, microwaves, infrared, ultraviolet. And of course, the big revelation is that if all those types of things, radio, TV, microwave, so on and so forth, if those are just different types of light, then you can actually manipulate them with circuits. Okay? In other words, this led to the technological revolution of realizing that you can control electromagnetic waves or light with circuits. So you can make things like radios, TVs, microwaves. So this was obviously a really a big revelation. So Maxwell kind of joins along with Galileo and Newton and Einstein as someone who really contributed an incredible amount to physics and science in general by basically realizing that light, study of light and the study of electromagnetism were not different fields of study. And the other thing I should tell you is that if you have a little bit more advanced math, you can combine all of these equations into one equation. So it's one equation for electromagnetism. So in fact, what we've been doing this whole course really is studying one single equation. So so that's a little bit of an overview. Hopefully in this course we may or may not get a chance to look at Maxwell's correction and take a look at EM waves. Hopefully we will, but not every semester we will. But this is kind of an overview of what we've done in the course and where you would go from there.